Okay guys, sorry I am not in class today. This was not expected. So we're just going to kind of continue where we let off. Now, every class was at a different spot when we were talking about natural logarithms on Friday. So wherever you're at, go ahead and fast forward until we get to the part where we stopped, and then pick up from there. So you don't have to re-look or re-listen to the stuff that we did on Friday. Okay, so we're just going to get going. So on Friday, we were talking about the derivative of logarithms, and we came up with two rules. Now, for an log log, the derivative is going to be that u prime over u with the natural log of the current base. Remember that a is a number. Okay. Now, for natural log, we get the same thing, but because this natural log of e is always going to be equal to 1. Remember, we talked about the natural log of e being equal to 1 on Friday. So ln of e equals 1. And because for a natural log, the base is always e, we'll always wind up with the natural log of e, which is equal to 1. So we get that the natural log derivative, not that, sorry. Let me do that really quickly. Undo that. Sorry, having malfunction this evening. Okay, so we get that the natural log function, the derivative of natural log, is at u prime over u. Very much like an log log, with the exception that the natural log of the base. We don't really need that with a natural log. Okay, function. So let's do a couple of examples. So for instance, the first example says the log of 4 of 3x plus 2. With a lot of the logarithms, we're using chain rule. Remember, that's where we got those rules from. So if we take the derivative of a logarithm, the first thing that I know is that the derivative of a logarithm is always going to give us a rational equation. So I'm going to start immediately there. So f prime of x equals, I'm going to start with my logarithm. Now, for an log log, I know I'm going to have a natural log. The base for this one is 4. So we're going to have the natural log of 4. So remember that that's a number. Now the original, that 3x plus 2, is going to go on the bottom. That's my u. And u prime gives us 3. That's the derivative of 3x plus 2. So there's our derivative. The next one, our g prime of x. Again, a natural logarithm. So we're going to wind up with a rational equation. I don't need the ln of the base because of the fact that we're already in ln, but my u still goes in my denominator. So sine x plus 3x, the original u. And then the derivative of that as a result of chain rule, our u prime, cosine of x plus 3. And there's my derivative. I'm done. The next one on the page, if I'm dealing with y prime, remember I can also write that as dy dx. Remember, those two things mean the same. I'm left with a rational, my original on bottom, and the derivative of that on top. And if we simplify that, that one can be simplified down to 2 over x. The next one, h of x, so h prime of x. We're dealing with an log log. So here's my rational. The current base is 3, so I'm going to have a natural log of 3. My original is that. And then, of course, the derivative of cosine of 2x. Well, that's my negative u prime, which is 2 cosine, sorry, not cosine. So negative 2 sine of 2x. Okay. Let's look at the last two on the page. So f of x, so my derivative, f prime, I'm dealing with the log log. Still going to end up with a rational. The natural log of the current base, which happens to be 5 here. My original. And of course the derivative on top. And the derivative of 2x plus 1 gives us 2. So I'm done. And the last one. So f prime of x, I'm dealing with a logarithm, so rational. This is an log log, so the natural log of 10 there. We have a x squared, that's my u, and u prime, which is 2x. And we can simplify this down, 1x on bottom, and on top cancel each other, so we wind up with 2 over x natural log of 10. And there's our derivative. Going to the next page. For some classes, I said go ahead and try this for homework. For other classes, we didn't even get to this part. So again, we've already gotten here, go ahead and fast forward to where it is that we ended. Okay. So it says if x equals ln of xy, find dy dx. Okay, so we're looking at an implicit equation because our x's and y's are mixed. If we don't remember our logarithm rules can actually help us and really break stuff down for us. So if we're dealing with a log of x times y, remember one of our log rules says we can rewrite that as log of x plus log of y. Okay. If we're dealing with log of x over y, we can rewrite this as log of x minus log of y. And if we're dealing with a log of x to some y, we can take that y value and drop it in front. Okay. So those are the log rules you learned first in Algebra 2, then of course in pre-cal. Now, if I was to take the derivative of this equation as is, I would have to use, of course, my chain rule as part of the natural log, but I'd also have to use a product rule. Now with logarithms, because of those 3 shortcuts here, these 3, I never really have to do a product rule or a quotient rule for any type of logarithm, because I can rewrite them like this one. So I'm going to rewrite this. This is x equals, have the natural log of x times y. So I'm going to use this rule right here to break it down and make it a little bit easier for what I'm about to do. So natural log of x plus natural log of y. And now I don't have to use a product rule at all. I can go straight to the derivative and take it term by term. So derivative of x gives us 1 equals the derivative of natural log of x, so again rational, u on bottom, derivative of u on top, so 1 over x, plus derivative of logarithm is a rational with a u on bottom and the derivative of y, which is dy dx. So now remember, for this problem we're solving for dy dx. So my first goal is to get everything that doesn't have a dy dx onto the opposite side of my equation. So the first thing I'm going to do is move over that 1 over x and subtract it out. So I get that equals dy dx over y. And I'm solving for dy dx, so I can multiply both sides by y. Be very careful here. If we're going to multiply, we need to multiply everything. So I'm just going to distribute that y. I get that. And dy dx. And there's my derivative. Let's look at the bottom of this page. So that's one of the problems. Sorry, I think I was on the wrong problem. So let's go back to that top problem right there. Sorry, I did this a little bit out of order. Okay, so the top one says, write the equation of the line tangent to the graph y equals 2x squared plus natural log of 3x minus 8 at the point where x is equal to 3. So the equation of a tangent line, remember that's 4 steps that we're doing. Our first step is, of course, to get the point. We have x equals 3, so we already know that we're looking at point 3. We have to figure out the y value. So if I'm going to figure out y, I'm going to plug in that 3 into the main equation. So 2 times 3 squared plus the natural log of 3 times 3 minus 8. So I get 18 plus the natural log of 1. Now the natural log of 1, remember on Friday we said the natural log of 1 is equal to 0. So this is going to 0 out. And we're left with 18. Oh, sorry, that was terrible. Let me fix that. So our point is 318. Okay, step 2 is to get the derivative, so y prime, or dy dx, whichever you prefer. I get 4x plus, and here's the derivative of the natural log. We're going to get a rational. Okay. Our original on bottom, and the derivative on top. So remember, the derivative of 3x minus 8 would give us back 3. That's our second step. There's no simplification needed. We're going to leave it as is. So our third step is to plug in to find y prime of that 3 that we're looking at. So everywhere there's an x, I'm plugging in a 3. So we get 12. And then, of course, plus 3 over 1, which gives us 15. So there is our, remember, our derivative represents the slope, so that's our m. And then, of course, the fourth and final is to figure out the actual equation of the tangent line. So y equals my slope times x minus my x value for my point, which was 3, plus the y value for my point, which was 18. And that's where we're going to leave it. So that kind of finishes up what we're doing from Friday. I know I gave these two examples as homework for a couple of the classes, and then the other class we didn't even get close to this. So I'm going to go back to that very first page, because on top of this, we're going to talk about the derivatives of exponentials. On Friday, I said this was my favorite derivative. Okay, I really like the derivative e to the x because it's the fastest and easiest derivative you'll ever take. So we're going to go back to page 76 in our journal. Okay, so it says, it starts off with saying, find f prime of x equals f of x equals to 4 raised to the x power by using logarithmic differentiation. And what that means is we can take any equation, so I'm going to rewrite it as y equals the natural log. Sorry, not natural log. Y equals 4 raised to the x. Now, we can change any exponential into, in fact, a logarithm. So that's the first thing I'm going to do. Okay. So I have a log of 4 equal to, not equal to, let's try that one more time. Base of 4, my argument is y, and it's equal to my exponent, which is x. And since I know the derivatives of logs, I can take the derivative of this using my implicit differentiation. So this is what I mean by logarithmic differentiation. We can change the problem into a log and derive the log problem instead of the exponential problem. So that's what I'm going to do. Okay, this is going to use implicit differentiation because my x's and y's, there's nothing I can do to separate them. And they're not really mixed here, but because we're taking the logarithm of the y value, that implicit differentiation is really important. So what I'm going to do is take the derivative of my left side of my equation. So I am dealing with a natural log of 4. My original is y, and the derivative of y is dy dx. That's a terrible dy dx. Okay. And then, of course, equal to, and the derivative of x gives us 1. Now if I'm solving for dy dx, I'm going to multiply both sides by my denominator. So I'd wind up getting y natural log of 4. I know what y is because we started off this problem with y equals to 4x, which means this derivative is actually the original equation times the natural log of the base. Well, that's interesting. The derivative of the exponential produces the exponential back. The only thing that changed is that new coefficient of the natural log of 4. And the reason we have that natural log of 4 is because of the fact that we turn this into a logarithm, and the part of differentiating a logarithm gives us a natural log. Okay. So if we think about it, if we take the derivative of, let's say, a to the u, remember a is a number. Let's go ahead and write that here. Let's change the color. So a is a number, which means the natural log of a would produce a number, much like the natural log of 4 in the previous problem. So the derivative of an exponential gives us back, change the color back to black, it gives us back itself times the natural log of the base. But because of the fact that I just took the derivative of u with respect to x, that invokes our chain rule, so our du dx. I don't like that du dx. Some people do. If it's u, go ahead and use it. I like u prime, so I always do my u prime in front. U prime, a to the u, natural log of a. So there is the derivative of an exponential, always. So let's highlight that. That's a new rule. That's rule number 13 out of our 17. Now, e to the u is an exponential. It's a special exponential that our base is e. E is the most important exponential base. And just like the natural log of the derivative of our natural log function, the derivative of e is more important than the derivative of any exponential because it's used more often. But it follows the same rule as the exponential in 1. So if you think about it, we're going to get u prime times original back and the natural log of the base, which is e. But the natural log of e, and because the base is always going to be e with these exponentials, the natural log of e is equal to 1. And we talked about that on Friday. So if we think about it, we get this, u prime of e to the u. So there's the derivative of the e exponential function. So again, a new rule, and we highlight our new rules. So that's exactly what I'm going to do. That's that one. So if we take the derivative of e, we pretty much get it back. He's kind of a loner because his derivative is exactly the same. It doesn't really change. The only thing that's going to change is that coefficient because of that u prime and because of chain rule. So let's look at a couple of examples. We're going to get through these pretty quickly using those two rules. So the derivative of f of x, or e's raised to the sine of x. Remember, that's one of our grouping symbols, exponents, which is why the chain rule applies here. So f prime of x, my u here is, of course, sine of x, which means my u prime is cosine of x. So if we put everything where it goes, our u prime goes in front, and we get back e, the original, the inside the same. And there's our derivative. Okay. Next one, y prime, not e, so we're going to have that extra natural log of the base at the end, like the first formula. So y prime, my u is 3x squared, so 6x is my derivative, times the original times the natural log of the base, which is 4 here. And there, I'm done. There's nothing you can really do to simplify these because you're dealing with a natural log of a number, variables. They're kind of crazy, so go ahead and just leave it as is. There's not going to be simplification needed. So let's look at the next one. H prime of x equals, we're dealing with exponential where the base is not e, so we're going to go back to our rule 1. Our original, or our u, is 3x squared plus 1. So u is 3x squared plus 1. If we take the derivative of that, we get 6x, much like the previous problem, times the original equation, the derivative of him does not change, and then times the natural log of the base. And there's our derivative. Okay. Now, this next one, a little bit weird, but 108 is a coefficient. So that 108 is a coefficient. We've been talking a lot about how these coefficients don't really change our process. We kind of just carry them along. So I'm going to do the same thing with this problem. Is I'm just going to carry that 108 down into our derivative. And if I can simplify it at the end, then I will. So y prime equals 108. Let me use some parentheses to help me out. Because really this is the piece, this 2 raised to the x over 12 is in fact our function. So that's what I'm going to derive. I don't like x over 12. That can get confusing, especially for our processes. It might make me think that I want to actually use the chain rule, and I don't want to do that. But if I pull out my coefficient to put them in front, that's a much better view because, again, that 1 over 12 is going to be a coefficient for us. So my u is at 1/12 x. So my u prime is 1 over 12. So that was our u. So our u prime was 1 over 12. Because much like the derivative of 3x is 3, derivative of 5x is 5, same thing there. So our u prime times the original times the natural log of the current base, which is 2. Now, if I can simplify, because I'm multiplying all the way across, I can multiply some numbers, like that 108 in front times that 1/12 actually gives us 9. And then he doesn't change, he stays the same. That's why he's all alone, like in my t-shirt above. And there we go, there's the derivative. Now the next example is a little bit more complicated because we're taking the derivative of the natural log and it involves an e. So we're just going to follow our rule starting with derivative of the outside, which is that natural log function. So we're going to take the derivative of the natural log. So we're going to get a rational. Natural log, base is e. I don't need that extra piece like in the previous part or the previous day. So really it's just my u. And then my u prime, the derivative of that is going to go on top. So the derivative of x is 1 plus, now my u is x squared here, my new u. So u prime times the original, e to the x squared. Yes, you can have an exponent raised to an exponent. That is a real thing. Okay. And now the last one, the last example, sorry. I don't know why I did that. Okay, so the last example on that page says, at what point does f of x equals e to the x over x have a horizontal tangent line? Ooh. Remember, horizontal tangent lines, anytime I see the word horizontal tangent line, I'm thinking my slope is equal to 0. Therefore, my derivative, so in this case, f prime of x, would be equal to 0. So I can figure out the point, so the x and the y, at which this is happening by using my derivative. So the first thing I want to do, of course, is take my derivative. Now I am dealing with the quotient, e to the x over x, or e to the x divided by x, which means I'm going to have to actually use my quotient rule. So derivative, f prime of x. Quotient rule says to take the derivative of the top. Well, the derivative of the top, I would be taking the derivative of e to the x my u is 1. Or sorry, my u is x, so my u prime is 1. So 1e to the x. Derivative of the top times the bottom minus derivative of the bottom times the top over the bottom squared. Now we talked about this a couple of days ago. We're dealing with a rational. Let me clean this up really quickly. Actually, no. E to the x is transcendental, and just like with all transcendentals, we like our transcendentals at the end, so I'm just going to rearrange that. That looks better. Now, we talked about rationals and the derivative being equal to 0. Remember, the derivative being equal to 0 comes from our denominator. Sorry, not our denominator, our numerator. I don't know what I'm thinking. So where our numerator is equal to 0. Okay, that's going to give us where our derivative is equal to 0. So really, all I'm going to do is take my numerator and solve. Remember, anytime we talk about solving in here, my first instinct should really be to factor this. So that's exactly what I'm going to do. They both have an e to the x in common, so I'm going to factor that out, and I get x minus 1. The great thing about factoring out e to the x is the fact that, and write this on the side, write it as on a post-it note, do something, because e to the x can never be two things. E to the x can never be 0, equal to 0, and e to the x can never be negative. If we recall our graph of e to the x, our graph of e to the x actually has a horizontal tangent line. I'm sorry, a horizontal asymptote at x equals 0. So it's never going to ever equal 0, and because it's above the x-axis, it's never going to be negative. So when we're factoring and we factor out an e to the x, we can actually cross him out. He cannot cause the function to be equal to 0 because he can never be 0. So we kind of ignore him when we're talking about factoring. So really, the only thing that's going to cause it to be 0 is where x minus 1 is equal to 0. So x is equal to 1. Now, it did say point, which means I need an x and a y. So since I have an x, I'm trying to find my y value. I go back to my main function and plug in 1. So e to the first power over 1 gives us just the number e. Remember, e is a number, about 2.7 couple digits. That's really all that matters. So really the point that I'm looking for is at 1, comma, e. And that's the point at which I have a horizontal tangent line. Okay, so after watching this video, go ahead and work on the next couple pages for the remainder of time that you have in class. If you have any questions, I will be back tomorrow on Tuesday, so just keep your questions and I'll get those answered first thing on Tuesday. Okay, have a